Okay, so what we have here is we've got uh, a rigid rod, a smooth rigid rod, which is fixed in XY plane. And here we have a slip ring of mass M, and it is kept at point A in the beginning. Coordinate of the point A and B given 0, comma L and L, comma 0. And we need and we are told to neglect gravity, and we need to determine the force acting on the particle given. And what we have to determine here is determine the minimum speed that must be given to the particle when it is at A so that it manages to reach B. So tell me what you will do in here. Any idea? Anyone? Wrong or correct? Just tell me what you think should be done. So we are supposed to find the minimum speed of the projection. So for minimum speed of the projection, is there something we can do about it? Anyone? Suppose if I'll ask you what is the minimum speed of the projection so that the particle reaches a certain height. For that, what do you do? Tell me. You consider reaching the particle at that height with zero speed for the minimum speed of the projection if I'm projecting it vertically upward. So is it the case something like that or it is different? If we are interested in projecting the particle with minimum speed. Okay, so if we'll try to solve it for the case that it must be reaching with the zero speed once it reaches B, that is going to be wrong here. Understanding it, if you will think in that manner that the minimum speed of the projection from A should be the one for which the particle reaches point B with zero speed, it is wrong or correct? Because I need to ask you some supporting argument for that, no? So whenever you get any question, don't jump into solving it by thinking it is going to belong to the category that you have seen already. So if I'll check out the forces at the point A and B, the force that will be acting on the particle. So one force will be normal contact force. Apart from that, the other force, this is this force. What it is going to be when I have particle at A. So when I have particle at A, the x coordinate 0, y coordinate is L. So the force is going to be acting only in the y direction. So whatever it may be, it is going to be acting only in y direction. And when the particle is at B, so as you can see, the force is kxi cap ayj cap. At point B, our y coordinate 0, so this force will be lying entirely in the x direction. Correct. Now, if I move from A to B, what you will find at A, I don't have any x coordinate, but as I move away from A towards B, the x coordinate will come into picture, and as I move further, the x coordinate will increase. The force will end up getting at a point A, the force is vertically upward. Afterwards, it will be inclined in this manner at some point, making some angle theta. And if you will see that, if I will consider taking out the point, which is the middle point of this rod. So what will be the coordinate of that middle point? You can tell, no, L by 2, L by 2. So if I'll ask you what is the force that will be acting when the particle is going to be, or what will be this force F when the particle will be at the middle of this rod, it's going to be F will be KL by 2 I cap plus KL by 2 J cap. And have, you must be knowing this thing that what angle this vector is going to be making from the horizontal. Can you tell me? It should not be wasting any time. Just by looking at it, you can tell, no? 45 degrees, both the components same, no?
Yes,
Correct.
sir.
So this angle is going to be 45 degrees. And you can even look and tell this angle is going to be 45 degrees. So when it will be at the middle point, maybe I'll name it as C. At middle point C, the force is perpendicular to the line AB. And before it, the force is inclined in this manner, because of which I am going to have a component in the direction B2, or I can say the force will be upside like that. And so what happens at A, we have x coordinate 0, only y coordinate there. So force is entirely lying in the y direction. And as I come down, the x coordinate increases, the force gets more and more inclined in other way. And here at C, it becomes totally perpendicular to the line. Now, after the point C, the x coordinate will be becoming more than the y coordinate. So the force will be inclined now in this manner or not. Suppose the angle theta somewhere here it has. So what you see is that after the middle point, force will be acting down. Or I can say the force is acting down the inclined plane kind of thing, correct? So what we have is before the middle point. So what is the direction in which our point mass will move? If it to be able to reach B, it must be moving down. So before the middle point C, I have a force which is opposing the motion, no? And after it crosses the middle point C, I have a force which is going to be supporting the motion of this rod. You understanding that point or not? Before this point, the force will be having a component which is acting towards it, because of which it will be opposing the motion of the point from A to B. But after point C, the force is going to be acting down the incline because and no, sorry, we have after the point C, the force has got a component down the incline always, because of which it will be supporting the motion of that slip ring once it crosses the middle point. So what we can say, once the ring will cross the middle point, it can move on its own. No, till C, I have to it is opposed to be moved down, but after C, it is supported to be moved along the path A to B, the straight line path A to B, correct? So what we can say, once the ring crosses the middle point, after that, it can move on its own, no? Or it can move itself. So what we do is the limiting case or the condition under which we must be projecting it with minimum speed so that it manages to reach B. So we are not interested in with what speed it reaches B. Only thing we are interested in is it should reach B. And what other thing we are interested in, we must be projecting it with minimum possible speed. So I hope all of you got that. No? So the minimum possible speed of the projection for which it reaches C, so for it reaches B, if projected from A, must be the one for which it reaches C with almost zero speed. But should know. Now, so what we will do, nothing much, work kinetic energy theorem only. No? What else we can do? Tell me. So work doesn't matter what is the nature of the forces, we don't need to look even to apply work kinetic energy theorem. And what is that? Net work done is going to be equal to change in kinetic energy. And what we are going to calculate the work done once the ring moves from A to C. So we want the ring to reach the middle point C with almost zero speed. So limiting case we consider it to be reaching with zero speed only. So it will be final or kinetic energy at C minus kinetic energy at A. Kinetic energy at C 0, and suppose it is projected with a speed V, so it will be minus of half mv square. Now to determine work done, we need to see what all forces acting on it. One will be the normal contact force, and the work done by it will be zero. Only next force is this force F. So just this force F will be doing work. So what we have is work done by this force F is going to be equal to minus of half mv square. And what kind of force it is? Variable with position. So what we do? We consider having a small change in position dr, which is tx I cap, dy j cap, and then we determine the work done for the small displacement, which will be kx dx plus ky dy. And after that, easy only to get net work done for an interval. We'll integrate it for with some proper limits. It will be kx dx plus ky dy equals to minus of half mv square. And you know what limits we are going to use. At point A, our x coordinate is 0, and at point C, the x coordinate is L by 2. At point A, the y coordinate is L, and at point C, the y coordinate is L by 2. It will become kx square by 2 limits from 0 to L by 2 plus of ky square by 2 limits from L to L by 2 equals to minus of half mv square. And then everything is known in here except v, and that will be the minimum speed of the projection for which the ring manages to reach the point B. After this, I think all of you can solve. No? You want, I can solve it. It's nothing left to solve now. So it will be KL square by 8 plus of KL square by 8 minus of KL square by 2 equals to minus of half mv square. So it's going to become KL square by 8 plus KL square by 8, KL square by 4 minus of KL square by 2. So will give us minus of KL square by 4 equals to minus of half mv square. So the minimum speed of the projection is going to be KL by 2m root over. Check that correct now? Well, if you understood this thing, what I'll do, I'll give you one example, something that you can relate to, which is going to be kind of same as the logic that we have applied here. So maybe I'll take a new page and there I'll discuss about that. And again, I'll come back to that page to give you time to copy. Suppose if I have one planet of mass m1, suppose, and there's another planet of mass m2. Now, the separation between these two planets also given to us, suppose r, and they're asking us, suppose, that determine the minimum speed of the projection of a particle from m1 so that the point mass, manages to reach m2. So tell me one thing, if at all I have to project something which I want it to reach m2 from m1, I will be projecting it from the side facing m2. Obviously, from here I'll not be projecting. That is one thing. So suppose if I have to project some mass of point mass m, so that we must be projecting it with the minimum possible speed, and we just want that particle to reach the other planet to this planet one, this planet two. So tell me, if I'll consider some point which is more nearer to the planet one, and what is the force that will be acting on our point mass? One will be the force because of one F1, and another will be F2. And if I am nearer to M1, then what we have is F1 is going to be more than F2. So we are going to experience a force which will be leftward or towards M1. Then as I start moving towards M2, what will happen? As we start moving
There
towards
will be
M2,
some force which will be
so
pulling us
say
backwards.
F1, wait, F1 will be decreasing and force because of 2 will be increasing or not. Even if you don't know how that Newton's laws of gravitation works, but at least you know more nearer that force will increase that force of gravity.
Yes, sir.
So F1 decreasing gradually, F2 increasing gradually. So there will come a time when F1 will become equal to F2. It's not like F2 will not be becoming equal to some number. It has to go through every number that will come in between. Correct. Suppose F1 is 10 units and F2 is 5 units somewhere. Then I move towards M2. F2 will increase, F1 will decrease. Somewhere both will become equal or not. So wherever the both will become equal at that point, so there will come a point where F1 will be equal to F2, where our net force is going to be zero. And there's a name for it. We'll be talking about it whenever we'll reach that chapter called neutral point. So at this point, both the forces are equal. And if I consider any point this side, the force will be in this side since F1 will be more than F2. So you can tell if I am on this side of this neutral point nearer to M2,
Force 2
F2
will
will
be.
be more than F1.
Yes, sir.
So net force will be towards M2. So it means if I have to project something which I want it to just reach M2, I don't care about with what speed it reaches M2. and but I care about the speed of projection should be minimum. So I must make that particle just to reach that neutral point. Because from beyond that neutral point towards M2, if at all it moves even a little further, the net force is towards M2 only. So after that, it can move on its own without us helping it. No.
Yes, sir. Without accelerating, it will go
So,
slow.
so it means the minimum speed of the projection for which the particle projected from M1 manages to reach M2 will be the one for which it reaches the neutral point with almost zero speed or just a speed little bit more than zero. So for limiting case, we'll consider it to be just zero speed. So same way, that middle point in this rod is doing that job of neutral point. Understood? No? We want the particle to move from A to B. Before it, I have some force always acting in a manner which opposes its motion down from A to B. But after point C, always I have a component which supports the motion of the ring from C to B. So if I will make that ring just to cross C, after that it can move on its own. All of you understood, no? To copy this thing, and once you're done copying it on me, then maybe I'll give you a minute to copy that one also. Then I'll start circular motion. Those who have missed classes, I don't know what they will do. They will do nothing. They'll get negative marks in the emails. What they will do. After coming to classes regularly and doing things properly, still people not getting desired marks. How come you can expect getting any marks in case if you even you don't do the minimum required thing? Copy after copy and tell me. We'll start we'll start circular motion, but we have to talk about few things like angular velocity and things like that. So what we have seen is in polar coordinate in 2D, we locate a particle using the distance it is going to be from a fixed point and the angle it is going to be making from a fixed direction. So suppose if I have that point moving in space, or suppose if that point is moving in this xy plane, so what all things can happen? R can change and theta can change, or both can change. Is it not? Suppose
Yes, sir.
if so, if I have a particle move to a new location, suppose P to P dash, so now it will be at some different distance, and now it will be making some different angle. So R becomes R dash, suppose, and the theta becomes theta dash, such that the change in the angle here is suppose d theta. So just like we had the average velocity, and then we had instantaneous velocity. So what we defined. So we'll talk about angular velocity. So it is going to be the rate of change of angle.
Theta minus dt by.
Correct. So before that, we must talk about angular displacement. Okay. First, we'll talk about angular displacement. What we have is, in this case, tell me the change in the angle that we have done here is, maybe I'll consider it to be delta theta. Change in the angle that we have done here is delta theta in magnitude. But what direction I should talk? I must be giving some direction to it. So one thing that we talk about is the sense in which we have given that angular displacement. So in this case, what is the sense in which we have given it? It is anti-clockwise sense, correct? But the problem with using anti-clockwise or clockwise is that is something it depends upon the position of the observer, no? Correct. Suppose the screen that you are looking at it, suppose it is a transparent one, it is a transparent board on which this particle moves from P to P dash. And from one side, the side from which you are looking at it, it is undergoing an angular displacement which is in anti-clockwise sense. Same particle, you observe it by being on the opposite side of the screen or the board. If you consider this thing written on the board, maybe a glass board, transparent one. So that same angular displacement, whatever you see anti-clockwise, will be clockwise from the other side or not.
Yes, sir.
There's a problem with clockwise and anti-clockwise because the moment I'll say something has undergone a displacement of this much angle clockwise, you will ask, sir, which side? Then I'll say left side. Then you'll say, sir, who's left? So much confusion. So to get rid of that confusion, we have brought a method to tell the direction, that is through right hand rule. So how we tell direction for the angular displacement is through right hand rule.
Right and thumb rule only, Nasa. You
Yeah,
showed in
correct. Yeah,
class.
yeah, correct. Yeah, we have discussed that thing in class. Just I'll repeat it a little bit. So what we do in this case to apply right hand rule, we curl our right hand fingers RHF, I'll write down, or RH fingers along the sense of rotation, and in doing so,
We will have anti-clockwise rotation, sir.
yeah, correct. Whichever way the right hand thumb points, that is the direction of mm, that is the direction of the vector, no? No, that is the direction of the angular displacement. Understood, no? So in this case, and obviously you're supposed to fold your fingers in the manner it is possible, not like you have to break your fingers like that. So here you try doing it, folding your fingers in the sense of rotation. You will see thumb will be pointing towards the z direction, no? In this case, correct? So in this given example, what we have is, I'll say the sense is going to be anti-clockwise, but the direction is going to be along plus z. This is how we will be giving direction to the angular displacement, but I have not used the word angular displacement vector. I have just told angular displacement because there's a catch here. This angular displacement is a vector quantity only when that angular displacement is infinitesimally small. In case if you have a displacement which is finite, it will have direction, but it will not be a vector quantity. Why? We will discuss it. I might have given that thing, I might have talked about it in vectors, but I may not have told why it is like that. I think so. We will discuss that today. So I'll write that point. Angular displacement is not a vector quantity if the angular displacement is finite. There's a reason for it. If at all something having direction and magnitude, that is necessary condition for it to be called as a vector. But there is not the sufficient condition. Sufficient condition is it must follow the algebra of the vectors. And if it doesn't follow any of the algebra, maybe triangle law, vector addition, that was not being followed by the electric current, so it was not a vector. So here it doesn't follow the commutative nature of vector addition. The reason it is, whenever the angular displacement is finite, it do not follows commutative nature of vector addition. And how it is, we see that through an example. So maybe you, whatever you have lying in front of you, something rectangular, maybe our modular book. Suppose if I have a, a book like this, that's, and then what I do is I'll give some directions to talk about. So this is X, Y, and Z. And suppose this is the front face of the book. This is the right one. This is the left one. This is top. This is bottom. And what we are going to do is we are going to do two displacements, two angular displacements which are going to be finite, but we'll be doing it in different order. So you know that if I add two vectors A and B, doesn't matter in what order we are going to add them, the result must be same only, no? Correct? And we have seen that thing through one example also. And now, so what I do here is I am going to provide two angular displacement. One time I will rotate this book by an angle which is, suppose I'll give this rotation is theta x by pi by 2 in anti-clockwise sense if I'm looking from positive x side. And next I'm going to rotate it along z axis. I'll name it as theta z. And here also I'm going to give a rotation of pi by 2 in anti-clockwise sense if I'm observing it by sitting at plus z side. So one time I will do this rotation first along x, then along z. Correct? Maybe I have got maybe this phone. If I will do one rotation, suppose this is my, it will be confusing in the camera. You try doing it that thing on your own. Whatever you have got lying in front of you, you try rotating it once along x and then along z and see what is the final figure looks like. And next you do the same rotation, but first you do it along z, then you do it along x and see the final figure how it looks like. And you will see that the final figure will not be same. Means effect of the adding the vector two vectors must not depend upon the order in which we have added those two vectors or order in which whatever those vectors do. Correct? No? See that everyone getting it same or different? Anything lying in front of you, do two rotations, one along x, pi by 2 anti-clockwise, then next along z, pi by 2 anti-clockwise. Next you do the same thing, but first you try doing the rotation along z, then along x. And you see the final figure coming same or different, Aswin? Rupesh coming same or different? Naveen?
Different.
Different, no? So
It's
what we
different.
see, different, no? So that is what I am trying to tell you. That theta x plus theta z will not be equal to theta z plus theta x. So it is not following commutative nature of vector addition whenever the angular displacement that we give is finite one. So in that case, the direction it will be having what direction, whatever told by right hand rule, but it is not going to be vector quantity and will be treated like a scalar. For example, if I ask you, there's a particle moving along a circular path, and if it starts at a point, and suppose the center of the circle is at origin, and particle starts from this point which is on the x-axis and undergoes one full rotation and again comes back to this final point at the same point. So what we have is, in this case, what will be the angular displacement? Tell me. So angular displacement will be 2 pi and its direction will be along plus z axis because what we do is anti-clockwise since it is going to be if I look it from this side. So you curl your right hand fingers, you see that the right hand thumb, if you curl your right hand fingers are its fingers in that sense, you will find the right hand thumb will be pointing in the plus z direction or not. So what is the nice thing about it, whether I observe this particle by being on the plus z axis side or whether I observe this particle by being on the minus z axis side, still the right hand thumb will come in same direction. No? You try think, imagining that if you're sitting at somewhere on the minus z axis side, so from this side, the same particle will look to be uh, undergoing motion in clockwise sense, correct? So from that side, even if you are observing it to be going in clockwise sense, still you apply the right hand rule, you will find the right hand thumb still will be pointing in the plus z direction. So because of this right hand rule, what we have is doesn't matter from whichever side I will be observing the particle, the direction of the vector will come unique, and it must come unique. The whole reason we tell direction is to avoid confusion, like which way the particle going and all. And again, if that confusion remains, then what is the point of that kind of convention to tell direction? Understood? No? So some clever kind of rule, is it not? Right hand rule. I don't know who invented it. It must have been intelligent guy, no? It is an indirect way to tell direction of a vector. So whichever vectors whose directions are given by right hand rule, no, those vectors are called axial vectors. But there is not something you need to know in physics. No one will ask you anything like that. But just for GK purpose, I'm telling you. And also, it is called pseudo vectors. Means this that displacement that particle does, whatever it does, it is in XY plane, living in XY plane, doing everything in XY plane. And why we talk about its direction to be in Z direction, anything. So that's why it is also called pseudo vectors. Understood? So I hope all of you understood angular displacement or not. That this part
Yes, sir.
basically. Okay, then copy this thing.
Sir, on
After copying, tell
23rd
me.
exam, circular motion will not be there, sir.
30th
29th,
exam,
sir.
30th exam.
ASA.
No, no, 30th it is changed. Date is changed. I got the
Sir, can you
notification.
repeat what is axial vector?
Whichever vector whose direction is given by right hand rule,
Okay, sir.
or also called axial vector. Some math kind of thing, not like anything like that is expected from you to know in physics. Okay. Okay, I can take a new page now.
Yes, sir.
Suppose if I have a particle going around in a circular path, and suppose it covers some angle in some given time, so the average angular velocity will be delta theta by delta t. No? Now, similar to the earlier things, instantaneous angular velocity will be, well, we'll use the symbol omega, and that will be limit delta t tending to 0, delta theta by delta t. That will be d theta by dt. And next we have angular acceleration. So we denote it by alpha. So average angular acceleration will be change in the angular velocity by the time interval, which is going to be a finite time interval. And instantaneous angular acceleration will be limit delta t tending to 0, delta omega by delta t. By definition, it will be d omega by dt. Okay.
Sir,
Now, please tell me.
sir, here theta can be both degree and in radians, sir.
No, no, radians only. No degree system we use in science. I told earlier on,
Okay, sir.
the radians only. Now direction of the angular velocity and angular acceleration is also given by the right hand rule. Suppose if I have a particle undergoing circular motion in anticlockwise sense, if I observe the particle by being somewhere on the plus z axis side, so what is the sense in which it is going to be moving is in clockwise and anti-clockwise sense. So what we do, we curl our right hand finger, same thing, no? RH means right hand fingers along the sense of rotation. In doing so, whichever way the right hand thumb points, that is going to be the direction of the vector, correct? And in this example, what we have is the sense that we have got is anti-clockwise. The direction that we are having is going to be plus theta. Suppose if I have a particle undergoing circular motion about the center of the circle, which is at origin, and the angular speed or the angular velocity with which it is doing that circular motion is omega. And suppose if I have the particle to be present at certain point, suppose here, okay, suppose at any point of time the particle is present at point A, and I'm asking you determine the angular velocity, determine the angular velocity with respect to the point B when the particle is at A. And what it is given is the particle performs or particle rotates with constant omega about origin around a circle of radius r. So even we can figure it out, not just when the particle is at point A, even we can do it even when the particle is going to be at any another point also. Suppose if I consider particle to be present at this point P at some point of time, so what exactly the rate of change of angle we take is what angle it is? The angle made by the position vector of the particle with respect to the reference line which crosses the fixed point that we consider in the polar coordinates. That is, see, we must be very clear about it. What is that theta is? So if I'll ask you, what is the theta, d theta by dt, which is omega is? So suppose at any point of time, the angle that this position vector of the particle makes with the position vector drawn from the origin. So the rate of change of this angle is our omega or not? Correct. So d theta by dt, that is our omega given. So if I want to find out at what rate the particle is rotating around point B, then we must first figure out the position vector of that particle with respect to point B. And nothing told we will be considering, or even anything if I consider still, if I consider the positive x to be our reference direction, the one that was considered for measuring theta. So the position vector making here is suppose phi. So what basically we are supposed to find here? We have to find d phi by dt, no? Getting the point. The angular velocity of the point P with respect to the B will be d phi by dt. That you get that, no, from the definition of what is our angular velocity is the rate of the change of the angle. What angle? The angle that it makes from the reference direction. So now you must have done some circle thing in like 9th, 10th class, and if you forget that, then why you did those things? So you know that now if this angle phi, this OB is the radius and OP is also the radius, so this angle will be also phi. And this is an external angle which is the sum of internal opposite angle, or what basically it is 2 pi minus t. This angle will be 2 pi minus phi. Sorry, 2 pi minus, not 2 pi, 180 degrees. No, so pi minus phi, pi minus 2 phi. So this angle theta will be pi minus of pi minus 2 phi. So what that angle theta is 2 phi. So what is given to us? The rate of change of theta, and what I have to find rate of change of phi. Correct? No? So what we will do, so we have got to find d phi by dt, and what we have got here is theta is equals to 2 phi. So phi is theta by 2, so it will become d by dt of theta by 2, half will come out since constant. D theta by dt is going to be omega, so it's going to be omega by 2. So that is even true when the particle will be at point A also. That is also true when the particle is at point P, any central point P also. So we can solve it by some another way also. But right now, this is the way by which you can solve at least. All of you understood this thing or not?
Sir, can you repeat it once again?
See, what exactly that d theta by dt omega is. The rate at which this angle theta changes is our omega. What theta? The angle made by the position vector of that point with what angle from where? From the reference direction. So what it is told is the particle is rotating with the angular velocity omega with respect to the origin. It means if I'll draw a position vector from O to P, the angle it is making at any point of time theta, so that d theta by dt is our omega. That you get that? No?
Yes, sir.
Now to find at what rate it is rotating about P, see what exactly rotation is. How fast it is going around that point without going away, without going towards it. How fast it is going around it. No? For that, what we must do? Common sense also tells us we must figure out the angle at what rate that angle phi must be changing. So here I considered the same reference direction. Now the angle, the position vector of the point P with respect to B making is suppose phi. So the rate at which that phi is going to change will be the angular velocity of point P with respect to B. Correct?
Yes, sir.
And phi equals to theta by 2, that you know theta will be equal to 2 phi. That you understood, no? In this triangle OBP, OB and OP are same length. So these two angles will be also same. That you know, no? So this angle will be pi minus 2 phi, and this angle will be theta, which is going to be pi minus 2 phi. What is that? Theta will be 2 phi. I have to find d phi by dt. I replaced pi with theta by 2. So half came out. D theta by dt given omega, so omega by 2. Understood, no?
Yes, sir. Thank you.
How much we have done? 4 pages only, no? Not even 4 pages, effectively 3 pages only. And how much time approximately it took? 50 minutes at least. That much only I'm asking you to come for extra classes, not like too much it is. This much you can handle anytime, no? So then, so if you have copied, we'll end the class here. So some people still absent today. Next class, it will be core circular motion. Don't forget to miss it. This is just the beginning of it. Okay. Now. Okay then. Bye everyone. See you in the next class. Naveen, you are joining now.
Thank you,
Okay,
sir.
class getting over.
No,
Then
sir.
you were there only.
No,
Then good.
sir. I've joined before, suddenly cut and now rejoined.
Okay. So you understood this one, no?
Ah, yes, sir. I noted also.
Okay. Okay.